In 1998, two teams of astronomers made a discovery that shattered our understanding of the cosmos and earned them the Nobel Prize in Physics. They found that our universe isn't just expanding, it's accelerating its expansion at an ever-increasing rate, driven by a mysterious force we call dark energy. This discovery presents one of the most profound paradoxes in modern physics. How can empty space itself possess energy that pushes the universe apart, and what does this mean for the ultimate fate of everything we know and love? If you're fascinated by these cosmic mysteries that challenge the very foundations of reality, make sure to subscribe to this channel and give a thumbs up. Your support helps me explore the deepest questions about our universe and existence itself. One quick question. If you could choose how the universe ends, would you prefer the Big Rip, the heat death, or the Big Crunch? Let me know in the comments below. I'll choose the most creative answer. The implications of dark energy are absolutely staggering. This mysterious force makes up roughly 70% of everything in the universe, yet we have no idea what it actually is. It's completely invisible, undetectable, except through its gravitational effects on the largest scales, and it seems to violate our most basic intuitions about how energy and matter should behave. If dark energy continues to dominate our cosmos, as it has for the past 5 billion years, our universe is heading toward a cold, empty, eternally expanding future where galaxies drift apart until they're lost beyond each other's cosmic horizons forever. But here's what makes this discovery truly mind-bending and paradoxical. Dark energy appears to emerge from the quantum vacuum itself, from what we consider to be completely empty space. According to quantum mechanics, what we call the vacuum of space is actually seething with virtual particles constantly popping in and out of existence in a cosmic dance of creation and annihilation. These quantum fluctuations should create a vacuum energy density, but when physicists calculate what this energy density should be based on our understanding of quantum field theory, they get a number that's 10 to the power of 120 times larger than what we actually observe through astronomical measurements. This represents the worst prediction in the entire history of science. To put this into perspective, imagine predicting that a person is 10 followed by 120 zeros, meters tall, when they're actually about 2 meters tall. The discrepancy is so enormous that it points to fundamental gaps in our understanding of quantum mechanics, general relativity, or both. Resolving this paradox could revolutionize physics in ways that make Einstein's discoveries look modest by comparison. The story of dark energy begins in the early 20th century when Albert Einstein first derived his field equations of general relativity in 1915. These elegant equations described how mass and energy curve spacetime, creating what we experience as gravity. But almost immediately, Einstein realized they predicted something that seemed impossible. The universe should either be expanding or contracting, not static and eternal as everyone believed at the time. The prevailing view in Einstein's era was that the universe was infinite, unchanging, and had existed in essentially the same state forever. Stars were born and died, but the overall structure remained constant. This static universe seemed so obvious that when Einstein's equations suggested otherwise, he assumed there must be an error in his theory rather than in humanity's cosmic perspective. To fix this apparent problem, Einstein introduced what he called the cosmological constant, represented by the Greek letter lambda. This was an additional term in his field equations that represented the energy density of empty space itself. This mysterious energy would provide a repulsive force to perfectly balance gravity's attraction on cosmic scales, keeping the universe stable and eternal. The cosmological constant was Einstein's attempt to preserve the static universe that everyone expected while maintaining the mathematical elegance of general relativity. Einstein's static universe seemed to solve the problem, but it was built on unstable foundations. The balance between gravitational attraction and cosmological repulsion was like trying to balance a pencil on its point. Any tiny perturbation would cause the universe to either expand or contract catastrophically. Despite this instability, the cosmological constant allowed Einstein to maintain consistency with the observations and expectations of his time. But Einstein's static universe was short-lived. In the 1920s, Edwin Hubble's groundbreaking observations of distant galaxies using the 100-inch telescope at Mount Wilson Observatory revealed that the universe was indeed expanding. By measuring the redshift of spectral lines from galaxies at different distances, Hubble discovered that galaxies farther from us were receding faster, following what became known as Hubble's law. The relationship was remarkably linear and precise. Double the distance to a galaxy and you double its recession velocity. This was exactly what you'd expect if space itself was stretching uniformly in all directions, carrying galaxies along like dots on an inflating balloon. The discovery meant that the universe had a history, a beginning, and was evolving over time. It also meant that Einstein's static universe was an illusion, and the cosmological constant was unnecessary. Einstein famously called the cosmological constant his greatest blunder, but the universe had other plans. What seemed like a theoretical mistake in 1917 would return decades later as the key to understanding our cosmic destiny. The expansion Hubble discovered wasn't just any expansion, it was the aftermath of what we now call the Big Bang, and as we'd eventually learn through painstaking observations, it was an expansion that was speeding up rather than slowing down as every physicist and astronomer expected. For most of the 20th century following Hubble's discovery, cosmologists worked under a reasonable assumption that the universe's expansion must be slowing down over time. After all, gravity is attractive, so all the matter scattered throughout the cosmos should be pulling back against the initial impetus of the Big Bang, fighting to halt the expansion like a ball thrown upward, eventually slowing due to Earth's gravitational pull. This led to one of the central questions in cosmology. Would there be enough matter in the universe to eventually halt the expansion and reverse it into what theorists called a big crunch? Or would the universe expand forever, gradually cooling and diluting as space continued to stretch? The answer depended on measuring the total density of matter and comparing it to a critical value that represents the dividing line between these two cosmic fates. If the actual density was above this critical value, gravity would eventually win the cosmic tug-of-war, and the universe would begin contracting, ultimately collapsing back into a singularity in a mirror image of the Big Bang. If the density was below the critical value, expansion would continue forever, but at an ever-decreasing rate as gravity's influence weakened over the growing cosmic distances. The critical density represents a knife-edge balance where the universe would just barely expand forever, with its expansion rate asymptotically approaching zero after infinite time. This perfectly balanced universe would be geometrically flat, neither curved like the surface of a sphere nor curved like a saddle, but perfectly Euclidean on the largest scales. Astronomers threw themselves into the challenge of measuring the universe's matter density. They counted stars in galaxies, estimated the mass of gas clouds, and tried to account for every possible source of matter they could observe. But when they added up all the visible matter in the universe, all the shining stars and glowing gas clouds they could detect with their telescopes, they came up dramatically short of the critical density. Even accounting for the mysterious dark matter that astronomers had discovered through its gravitational effects on galaxy rotation curves and galaxy cluster dynamics, the total matter density seemed to be only about 30% of the critical value. This suggested we lived in what cosmologists call an open universe that would expand forever, gradually cooling and diluting as space stretched toward infinity. The discovery of dark matter itself had been one of the great puzzles of 20th century astronomy. When astronomers measured how fast stars orbit in the outer regions of galaxies, they found speeds that were far too high for the amount of visible matter present. According to Newton's laws, these stars should have been flung out into intergalactic space long ago. The only explanation was that galaxies contain roughly 5 times more matter than we can see, matter that interacts gravitationally but doesn't emit, absorb, or scatter light in any detectable way. Galaxy clusters provided even more dramatic evidence for dark matter. When astronomers used gravitational lensing to weigh entire clusters of galaxies, they found that the total mass was many times greater than all the visible stars and gas combined. The dark matter seemed to form an invisible scaffolding that held cosmic structures together, but its nature remained completely mysterious. Despite the discovery of dark matter, the total matter budget of the universe still fell short of the critical density. Cosmologists began to accept that we lived in an open, eternally expanding universe. But they still expected that this expansion would be decelerating due to the gravitational pull of all the matter, both visible and dark, scattered throughout space. Then came 1998 and the discovery that changed everything we thought we knew about the universe. 2 independent teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory and the High Z Supernova. Search team led by Brian Schmidt at the Australian National University and Adam Rees at Johns Hopkins University were using Type Ia supernovae as standard candles to measure the expansion history of the universe across cosmic time. Type Ia supernovae are among the most violent and spectacular events in the cosmos. They occur when a white dwarf star, the dense remnant of a sun-like star, accumulates matter from a companion star until it reaches a critical mass of about 1.4 solar masses. At this point, the white dwarf undergoes a runaway nuclear explosion that completely destroys the star, briefly outshining an entire galaxy of hundreds of billions of stars. What makes Type I supernovae so valuable for cosmology is their remarkable consistency, because they all involve white dwarfs exploding at essentially the same critical mass. They all reach nearly the same peak brightness. This makes them ideal cosmic lighthouses for measuring distances across billions of light years. By comparing their apparent brightness to their known intrinsic brightness, astronomers can calculate how far away they are with remarkable precision. The plan for both supernova teams was elegantly straightforward. Observe Type Ia supernovae at different distances and therefore at different times in cosmic history, and see how the universe's expansion rate had changed over time. If expansion was slowing down due to gravitational deceleration, distant supernovae would appear brighter than expected because the universe would have been smaller in the past than predicted by a model with constant expansion rate. If expansion was perfectly constant, the observations would match a steady expansion model exactly. What both teams found defied all expectations and overturned decades of cosmological assumptions. The distant supernovae appeared significantly dimmer than predicted by either deceleration or constant expansion scenarios. This meant they were farther away than anyone had anticipated. Instead of slowing down over cosmic time, the universe's expansion was actually speeding up, accelerating at an ever-increasing rate. Something was pushing space apart with ever-growing strength, overwhelming gravity's attractive pull on the largest cosmic scales. This discovery introduced the concept of dark energy to the world, though the name itself highlights our profound ignorance about its true nature. We call it dark because it doesn't emit, absorb, or reflect electromagnetic radiation of any wavelength. We call it energy because it has the gravitational effect of energy in Einstein's field equations, but we have absolutely no idea what it actually is at a fundamental level. The 1998 discovery was so unexpected and revolutionary that both teams spent months double-checking their observations and calculations, looking for any possible error that might explain away this bizarre result. They considered whether dust in distant galaxies might be dimming the supernovae, whether the supernovae themselves might have been intrinsically different in the distant past, or whether some unknown systematic effect was throwing off their distance measurements. But every test they performed confirmed the same shocking conclusion: the universe's expansion is accelerating, and has been for approximately the past 5 billion years. About halfway through cosmic history, something began pushing space apart faster and faster, transition from the expected deceleration phase to the current epoch of acceleration. The implications were staggering. Dark energy couldn't be just a minor component of the cosmos. To drive the observed acceleration, it had to dominate the universe's energy budget, making up roughly 70% of everything that exists. This meant that the vast majority of our universe consists of something we don't understand at all. The observations since 1998 have only strengthened the case for dark energy while simultaneously deepening the mystery surrounding its nature. The cosmic microwave background, the afterglow radiation from the Big Bang that fills all of space, has been measured with exquisite precision by a series of sophisticated satellite missions, including the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and most recently the European Space Agency's Planck satellite. These precision measurements of the cosmic microwave background confirm that our universe contains approximately 5% ordinary matter, the protons, neutrons, and electrons that make up atoms, 25% dark matter, and 70% dark energy. These percentages have been verified and refined by multiple independent methods, from large-scale galaxy surveys to gravitational lensing studies, to observations of distant supernovae and gamma-ray bursts. But here's where the dark energy paradox becomes truly bewildering and challenges our understanding of fundamental physics. If dark energy is simply Einstein's cosmological constant, then it represents the energy density of the vacuum of space itself. According to quantum field theory, our most successful description of particles and fundamental forces, empty space should indeed possess energy due to quantum fluctuations that are required by Heisenberg's uncertainty principle. In quantum field theory, even the vacuum state of space contains what are called zero-point fluctuations. Virtual particles constantly appear and disappear in pairs throughout the vacuum, borrowing energy from the quantum fields and paying it back so quickly that Heisenberg's uncertainty principle allows the transaction. Every quantum field contributes to this vacuum energy, and every possible wavelength of fluctuation adds to the total. When physicists attempt to calculate the energy density this should create, they encounter one of the most embarrassing failures in the history of theoretical physics. The quantum vacuum energy density should be approximately 10 to the 120 power times larger than the observed dark energy density. This isn't just wrong by a small factor, it's wrong by more than the number of atoms in the entire observable universe. To put this catastrophic disagreement in perspective, imagine trying to predict the height of a person and getting an answer that's larger than the observable universe when the person is actually about 2 meters tall. It's as if quantum field theory is telling us that the vacuum energy should be so enormous that it would curve space-time so severely that the universe couldn't exist. Yet observations show that it's just barely large enough to drive the gentle acceleration we observe. This spectacular failure of theoretical prediction points to fundamental gaps in our understanding of quantum mechanics, general relativity, or both theories. Either quantum field theory is dramatically wrong about vacuum energy in ways we don't understand, or there's some unknown physical mechanism that cancels out almost all of this energy while leaving just the tiny residual amount we observe as dark energy. Both possibilities challenge the foundations of modern physics and suggest that our two most successful theories are incomplete in ways that could require revolutionary new insights to resolve. The cosmological constant problem, as this discrepancy is known throughout the physics community, is often called the worst prediction in the history of science, but it's much more than just an embarrassing calculation error. The problem suggests that either our understanding of quantum vacuum fluctuations is fundamentally flawed, or there exists some symmetry or mechanism in nature that we haven't discovered yet that precisely cancels the vacuum energy to leave only the observed dark energy density. Some physicists have proposed that supersymmetry, a hypothetical symmetry between matter and force particles, might provide such a cancellation mechanism, but searches for supersymmetric particles at the Large Hadron Collider have so far come up empty. Alternative approaches to the cosmological constant problem have led physicists to propose that dark energy isn't constant at all, but instead changes over time, driven by a dynamic quantum field that pervades all of space. This hypothetical field has been dubbed quintessence, named after the fifth element in ancient Greek philosophy that was thought to compose the heavenly spheres. Unlike Einstein's cosmological constant, which has perfectly constant energy density throughout space and time, quintessence would be a scalar field that could vary as the universe evolves. The field would have potential energy, like a ball rolling on a landscape of hills and valleys, and its motion through this potential would determine how the dark energy density changes over cosmic time. Quintessence models offer the appealing possibility that dark energy could speed up or slow down over cosmic history, potentially even changing sign to become attractive rather than repulsive. This opens up entirely new possibilities for the universe's ultimate fate, from eternal acceleration to eventual contraction and collapse in a big crunch. But quintessence faces its own severe fine-tuning problems, requiring the field's mass and potential energy function to be adjusted with extraordinary precision to match current observations. The quintessence field would need to have an incredibly tiny mass, many orders of magnitude smaller than any other field known to physics, to avoid oscillating rapidly and averaging to zero over cosmic timescales. Its potential energy function would need to be almost perfectly flat, with an incredibly shallow slope that allows the field to roll slowly enough to drive acceleration for billions of years without either stopping or accelerating too rapidly. This fine-tuning is so extreme that many physicists find quintessence models just as problematic as the cosmological constant itself. Why should nature provide a scalar field with exactly the right properties to drive cosmic acceleration at exactly the epoch when intelligent observers like ourselves exist to discover it? This leads to what cosmologists call the coincidence problem. Why did dark energy begin to dominate the universe just a few billion years ago, rather than much earlier or much later in cosmic history? Other theoretical approaches propose that dark energy emerges from modifications to Einstein's general relativity itself on the largest cosmic scales. Perhaps the theory of gravity that works perfectly well in the solar system and for describing black holes breaks down when applied to distances of billions of light years, and what we interpret as dark energy is really a signature of new gravitational physics operating on cosmic scales. These modified gravity theories, with names like FR gravity, DGP gravity, and Diwali-Gabadadze-Parati models, face the formidable challenge of explaining why gravity would change its behavior at precisely the scale where dark energy effects become important. They must also pass stringent tests from solar system observations, which have confirmed Einstein's general relativity to extraordinary precision, while producing exactly the right amount of apparent acceleration on cosmological scales. Some modified gravity models propose that our universe is embedded in a higher dimensional space, with gravity leaking into these extra dimensions on the largest scales. Others suggest that gravity itself is an emergent phenomenon that behaves differently when averaged over cosmic volumes. While these ideas are theoretically fascinating, they face significant challenges in producing specific, testable predictions that distinguish them from dark energy models. The phantom dark energy scenario presents perhaps the most disturbing possibility for our cosmic future. In this model, dark energy density actually increases over time rather than remaining constant, leading to a runaway acceleration that would eventually tear apart every structure in the universe. The acceleration would become so strong that it would overcome not just gravity, but eventually all the fundamental forces that hold matter together. In the phantom scenario, the universe's expansion would accelerate at an ever-increasing rate. First, galaxy clusters would separate beyond the point where their mutual gravitational attraction could hold them together. Then individual galaxies would be stretched apart as space expanded faster than light could travel between their constituent stars. Solar systems would be disrupted as the expansion overcame the gravitational bonds holding planets in orbit around their stars. Eventually, even atoms themselves would be ripped apart as the accelerating expansion of space overcame the electromagnetic forces that bind electrons to nuclei. This ultimate cosmic catastrophe has been dubbed the Big Rip by cosmologists, and it represents perhaps the most violent possible ending for our universe. Current observations cannot yet distinguish between constant dark energy and slowly evolving phantom energy, but future precision measurements might reveal which scenario awaits us. Current astronomical observations are not yet sensitive enough to distinguish definitively between constant dark energy, slowly evolving quintessence, or phantom energy scenarios. The differences between these models would only become apparent when measured over cosmic timescales of billions of years, requiring observations of unprecedented precision across vast reaches of space and time. Future astronomical surveys are being designed specifically to address these questions with revolutionary new capabilities. The European Space Agency's Euclid Space Telescope, launched in 2023, will map billions of galaxies across cosmic time to trace the expansion history with extraordinary precision. By measuring both the distances to galaxies through their apparent brightness and their recession velocities through redshift, Euclid will determine whether dark energy density has remained constant or evolved over cosmic history. The Nancy Grace Roman Space Telescope, formerly known as the Wide Field Infrared Survey Telescope, and scheduled for launch in the mid-2020s, will conduct the most precise dark energy survey ever attempted. By observing thousands of Type Ia supernovae across a wide range of cosmic distances and measuring weak gravitational lensing effects across huge areas of sky, Roman will determine whether dark energy's equation of state parameter differs from the value of -1 predicted for a pure cosmological constant. Ground-based surveys like the Vera Rubin Observatory's Legacy Survey of Space and Time will complement these space missions by observing the southern hemisphere with unprecedented depth and precision. The survey will discover millions of supernovae and map billions of galaxies over the course of a decade, creating a detailed time-lapse movie of how cosmic structure has evolved over the past 10 billion years of cosmic history. The quantum origins of dark energy connect to some of the deepest and most fundamental puzzles in all of physics. In quantum field theory, the theoretical framework that describes all known particles and forces except gravity, even completely empty space, contains zero-point fluctuations that represent the minimum energy required by Heisenberg's uncertainty principle. These quantum fluctuations are not just mathematical abstractions, but have real, measurable effects that have been confirmed in laboratory experiments. The Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948, demonstrates that quantum vacuum fluctuations can produce measurable forces between closely spaced conducting plates. When two uncharged metal plates are brought very close together in vacuum, quantum fluctuations with wavelengths longer than the separation between the plates are excluded from the region between them, while shorter wavelengths can exist both inside and outside. This creates a net pressure that pushes the plates together, and this tiny force has been measured in sensitive laboratory experiments. Every quantum field that exists in nature contributes to the vacuum energy density. The electromagnetic field contributes through virtual photons, the weak nuclear force through virtual W and Z bosons, the strong nuclear force through virtual gluons, and matter fields through virtual electron-positron pairs and other particle-antiparticle pairs. When physicists attempt to add up contributions from all possible fields and all possible wavelengths of quantum fluctuations, the result diverges to infinity. Physicists have developed sophisticated mathematical techniques called renormalization to handle these infinities in quantum field theory calculations. The basic idea is to subtract away the infinite parts in a carefully controlled way to obtain finite, measurable predictions for particle interactions and decay rates. This procedure works beautifully for calculating the properties of particles and forces, yielding some of the most precise predictions in all of science. But renormalization fails spectacularly when applied to gravity and cosmology. Unlike other forces, gravity couples to all forms of energy and momentum, including the vacuum energy density. In Einstein's general relativity, the vacuum energy contributes directly to the curvature of spacetime through the stress energy tensor that appears on the right-hand side of the field equations. This means we cannot simply subtract away the vacuum energy as we do in other quantum field theory calculations. The vacuum energy density should curve spacetime so severely that the universe would either collapse immediately or expand so rapidly that no structures could ever form. The fact that we exist in a universe where galaxies, stars, and planets can form and persist for billions of years tells us that the effective vacuum energy density must be incredibly tiny compared to theoretical predictions. String theory, the leading candidate for a unified theory that would merge quantum mechanics with general relativity, offers new perspectives on the cosmological constant problem, though it has not yet provided a definitive solution. In string theory, the fundamental constituents of reality are not point particles, but tiny vibrating strings existing in a space with additional dimensions beyond the familiar three of space and one of time. Our four-dimensional spacetime emerges from a higher dimensional space where strings vibrate in incredibly complex patterns. The vacuum energy in this framework depends on how the extra dimensions are curled up or compactified, potentially offering a way to naturally suppress the cosmological constant to small values through the geometry of these hidden dimensions. But string theory also predicts the existence of what theorists call the landscape, an enormous collection of possible vacuum states corresponding to different ways the extra dimensions can be compactified. Current estimates suggest there may be as many as 10 to the 500th power different possible universes with different physical constants, different particle masses, and crucially, different amounts of dark energy. This vast landscape has led some physicists to propose that we live in a multiverse where the vast majority of regions have huge cosmological constants that prevent the formation of any interesting structures, and we find ourselves in one of the incredibly rare regions where dark energy is small enough to allow galaxies, stars, and ultimately life to exist and evolve over billions of years. The anthropic principle in this context suggests that dark energy's observed value is determined not by fundamental physics alone, but by the additional requirement that intelligent observers like ourselves must be able to exist to measure it. In universes with much larger dark energy densities, acceleration would have begun so early in cosmic history that matter could never have clumped together under its own gravity to form the first generation of stars and galaxies. In universes with negative cosmological constants, the attractive dark energy would cause cosmic collapse so quickly that there wouldn't be enough time for the nuclear processes inside stars to synthesize the heavy elements necessary for rocky planets and complex chemistry. Only in the narrow range where dark energy is small and positive could a universe like ours exist with billions of years of stable expansion, allowing for the formation of complex structures and ultimately intelligent life. This anthropic explanation is deeply unsatisfying to many physicists because it seems to abandon the goal of finding a fundamental, first principles explanation for why dark energy has the value it does. Instead of deriving the cosmological constant from the basic laws of physics, anthropic reasoning argues that we shouldn't be surprised to find ourselves in a universe where the cosmological constant is small enough to permit our existence, since we obviously couldn't exist in universes where it's too large. The debate over whether anthropic reasoning represents valid science, or a retreat from the fundamental goal of understanding why nature has the properties it does, continues to divide the physics community. Critics argue that anthropic explanations are not truly scientific because they cannot be tested or falsified, while supporters contend that if we really do live in a multiverse, then anthropic selection might be the only way to understand why our particular cosmic region has the properties it does. Loop quantum gravity represents an alternative approach to quantum gravity that suggests space-time itself might be discrete at the smallest scales rather than the continuous fabric described by Einstein's general relativity. In this framework, space is made of quantum loops that create a granular structure below the Planck length, the incredibly tiny scale where quantum gravitational effects become important. This granular structure might naturally regulate the vacuum energy density, preventing it from diverging to infinite values as it does in conventional quantum field theory. The discrete nature of space at the Planck scale could provide a natural ultraviolet cutoff that limits the contribution of short-wavelength quantum fluctuations to the vacuum energy. While loop quantum gravity has not yet provided a complete solution to the cosmological constant problem, it offers a promising direction for understanding how quantum effects might be tamed at the intersection of gravity and quantum mechanics. The holographic principle, which emerged from the study of black hole physics, proposes that all the information contained in a volume of space can be encoded on its two-dimensional boundary surface. Applied to cosmology, this radical idea suggests that our three-dimensional universe might actually be encoded on a distant two-dimensional surface, fundamentally changing how we think about vacuum energy and the structure of space-time itself. If the universe is truly holographic in nature, then the vacuum energy problem might be resolved by recognizing that our three-dimensional picture of quantum field theory is incomplete or even illusory. The true degrees of freedom might live on a lower dimensional boundary, where the calculation of vacuum energy might give sensible results that match observations. The holographic principle has led to remarkable insights in theoretical physics, including the ADS/CFT correspondence discovered by Juan Maldacena, which provides an exact mathematical relationship between a theory of gravity in one space and a quantum field theory in a space with one fewer dimension. While these results apply to special types of curved spacetimes rather than our actual universe, they demonstrate that holographic ideas can provide precise, calculable insights into the relationship between gravity and quantum mechanics. Observational tests of dark energy continue to push the boundaries of precision cosmology, with each new measurement either confirming our current understanding or potentially revealing cracks that point toward new physics. Type Ia supernovae remain crucial standard candles for tracing cosmic expansion, but astronomers have discovered that these stellar explosions show subtle variations that must be carefully understood and calibrated to use them as precise distance indicators. Environmental effects, such as the metallicity of the exploding white dwarf and the properties of its stellar companion can influence the peak brightness of Type 1a supernovae. Evolutionary changes over cosmic time, as the stellar populations that produce these explosions change their properties, introduce additional uncertainties that must be modelled and corrected. Despite these challenges, large samples of supernovae, observed with space-based telescopes, continue to provide some of the most precise measurements of dark energy's properties. Baryon acoustic oscillations provide a completely independent method for mapping the universe's expansion history that doesn't rely on standard candles like supernovae. These are fossilized imprints of sound waves that propagated through the hot, dense plasma of the early universe before atoms formed about 380,000 years after the Big Bang. When atoms finally formed and the universe became transparent to light, the sound waves froze in place, leaving behind a characteristic scale imprinted in the distribution of matter. This scale, about 500 million light-years in the current universe, serves as a standard ruler that allows astronomers to measure how space itself has stretched over cosmic time. By mapping the three-dimensional positions of millions of galaxies and measuring how the Baryon acoustic oscillation scale has changed with cosmic epoch, astronomers can trace the expansion history with exquisite precision and determine whether dark energy density has evolved over time. The Sloan Digital Sky Survey and its successors have mapped millions of galaxies to measure baryon acoustic oscillations across multiple cosmic epochs. The BOSS survey, completed as part of SDSS-3, provided some of the most precise measurements of dark energy properties ever achieved. Future surveys like the Dark Energy Spectroscopic Instrument will extend these measurements to even larger volumes and greater precision. Gravitational lensing offers yet another powerful probe of dark energy through its effects on the growth of cosmic structure over time. As the universe accelerates due to dark energy, the gravitational pull of dark matter halos becomes less effective at pulling additional matter together to grow into larger structures. This suppresses the growth rate of cosmic structure in a way that can be measured through how strongly galaxy clusters and massive halos bend light from background galaxies. Weak gravitational lensing, where the distortion of background galaxy shapes is too small to see by eye, but can be measured statistically across large samples, provides a direct probe of how matter has clumped together over cosmic history. The technique is sensitive to both the expansion rate of the universe and the growth rate of structure, providing a powerful test of dark energy models and modified gravity theories. The Dark Energy Survey, completed in 2019 after 6 years of observations, mapped 300 million galaxies to measure weak lensing, galaxy clustering, and supernovae simultaneously. The combination of multiple probes provides much stronger constraints on dark energy properties than any single method alone, and the results have confirmed the basic picture of cosmic acceleration while placing tight limits on possible variations in dark energy density over time. The cosmic microwave background provides our most precise snapshot of the universe when it was only 380,000 years old, long before the first stars formed. The tiny temperature fluctuations measured by the European Space Agency's Planck satellite encode information about the geometry and contents of the universe with extraordinary precision. These measurements confirm that we live in a spatially flat universe with exactly the matter and energy densities required by dark energy models. But the cosmic microwave background has also revealed intriguing tensions between different cosmological measurements that hint at the possibility of new physics beyond the standard model. The Planck measurements predict a Hubble constant, the current expansion rate of the universe, of about 67 kilometers per second per megaparsec. However, direct measurements using Cepheid variable stars and type Ia supernovae in the nearby universe give a value of about 73 kilometers per second per megaparsec. This Hubble tension represents about an 8% disagreement that might seem small, but it's statistically highly significant given the precision of both measurements. The disagreement could indicate that our standard cosmological model is incomplete, potentially requiring new physics in the dark sector, modifications to general relativity, or exotic properties of neutrinos or other particles. Some proposed solutions to the Hubble tension involve modifications to dark energy, such as models where dark energy was present even in the early universe and affected the cosmic microwave background in subtle ways. Other proposals suggest that dark matter interacts with photons or neutrinos in ways we haven't accounted for, changing how structure formation proceeds and affecting the relationship between early and late-time measurements. The resolution of the Hubble tension could provide crucial clues about the nature of dark energy and dark matter. If the disagreement persists as measurements become even more precise, it would strongly suggest that our current model of cosmology is missing important physics. Alternatively, if systematic errors in one or both measurements are identified and corrected, it would strengthen our confidence in the standard model of cosmology. Galaxy surveys operating across multiple wavelengths of light are creating the most detailed maps of cosmic structure ever achieved. The Dark Energy Spectroscopic Instrument, which began operations in 2021, will measure precise redshifts for 35 million galaxies and 2.4 million quasars over 5 years of observations. This enormous dataset will trace cosmic expansion and structure growth from the present day back to when the universe was less than 2 billion years old. The European Space Agency's Euclid mission, launched in July 2023, will complement ground-based surveys by observing from space with exceptional image quality and wavelength coverage. Euclid will measure the shapes and redshifts of billions of galaxies, mapping dark matter through weak gravitational lensing while simultaneously tracing the expansion history through galaxy clustering and baryon acoustic oscillations. The combination of Euclid's space-based observations with ground-based surveys will provide unprecedented statistical power for testing dark energy models. The surveys will be sensitive to the equation of state parameter W, which relates dark energy's pressure to its energy density. For Einstein's cosmological constant, W equals exactly -1. For quintessence models, W could range from 0 down to -1, while phantom dark energy requires W less than -1. Current observations constrain W to be very close to -1, consistent with a cosmological constant, but with uncertainties large enough to allow for significant deviations. Future surveys will measure W with precision better than 1%, potentially detecting small deviations that could reveal the dynamic nature of dark energy and provide clues about its underlying physics. The Nancy Grace Roman Space Telescope will conduct the most comprehensive dark energy survey ever attempted when it launches in the mid-2020s. Roman's wide field of view and exceptional sensitivity will enable simultaneous measurements of Type Ia supernovae, weak gravitational lensing, galaxy clustering, and baryon acoustic oscillations across unprecedented volumes of space and cosmic time. Roman will discover and monitor thousands of supernovae across a range of redshifts, providing the most precise measurements ever achieved of how cosmic expansion has evolved over the past 10 billion years. The telescope's infrared capabilities will allow it to observe supernovae that are too distant and redshifted for ground-based optical surveys, extending measurements deep into the epoch when dark energy was just beginning to dominate cosmic dynamics. Gravitational wave detectors have opened an entirely new window on the universe that could reveal dark energy's properties in unexpected ways. When black holes or neutron stars merge anywhere in the observable universe, they emit ripples in space-time itself that carry information about the expansion rate at the time and location of the merger. As gravitational wave astronomy matures over the next decades, these cosmic collisions could provide what astronomers call standard sirens that complement supernova and other distance measures. The Laser Interferometer Gravitational Wave Observatory has already detected dozens of black hole mergers and several neutron star collisions, opening up multi-messenger astronomy where the same cosmic event is observed through both gravitational waves and electromagnetic radiation. When LIGO detected gravitational waves from merging neutron stars in August 2017, telescopes around the world observed the optical and gamma-ray counterpart, providing the first standard siren measurement of the Hubble constant. Future gravitational wave detectors will be sensitive to mergers throughout cosmic history. The European Space Agency's Laser Interferometer Space Antenna, scheduled for launch in the 2030s, will detect gravitational waves from space with arms stretching millions of kilometers. LISA will be sensitive to supermassive black hole mergers across the entire observable universe, potentially providing standard siren measurements back to when the universe was less than 1 billion years old. The combination of gravitational wave and electromagnetic observations of the same events will provide powerful new tests of dark energy models. If dark energy affects the expansion rate differently than predicted by Einstein's cosmological constant, these effects should be detectable in the relationship between gravitational wave distances and electromagnetic redshifts measured for the same sources. Fundamental physics experiments conducted in terrestrial laboratories are also probing the nature of dark energy through ultra-precise tests of gravity and searches for new forces that might be associated with quintessence or other dynamic dark energy models. If dark energy arises from a new scalar field like quintessence, this field might produce extremely weak but detectable forces that could be measured in sensitive experiments. Tests of Newton's inverse square law of gravity on sub-millimeter scales use torsion balances and atomic interferometers to search for deviations that might indicate extra dimensions or modifications to general relativity. While no deviations have been detected so far, the sensitivity of these experiments continues to improve, potentially reaching levels where quintessence-type interactions might become detectable. Atomic interferometry experiments can measure gravitational effects with extraordinary precision by using lasers to manipulate the quantum wave nature of atoms. These experiments are sensitive to accelerations smaller than 1 part in a trillion of Earth's surface gravity, making them potentially sensitive to the kinds of new forces that some dark energy models predict. The implications of dark energy extend far beyond cosmology to touch on the most fundamental questions about the nature of space, time, consciousness, and existence itself. If empty space truly possesses energy density that drives cosmic acceleration, what does this tell us about the quantum vacuum state and the fundamental structure of reality? Why is the observed vacuum energy density so incredibly much smaller than theoretical predictions suggest it should be? These questions force us to confront deep philosophical issues about the nature of physical law and the relationship between mathematics and reality. Is the universe somehow fine-tuned to allow the existence of complexity and consciousness? Or do we live in one region of a vast multiverse where the physical constants take on all possible values, with intelligent observers naturally finding themselves in regions where the constants permit their existence? The anthropic principle raises profound questions about the role of observation and consciousness in determining physical reality. Some interpretations of quantum mechanics suggest that conscious observation plays a fundamental role in collapsing quantum wave functions and determining the properties of physical systems. Could the existence of conscious observers somehow influence the value of the cosmological constant through quantum mechanical effects that we don't yet understand? These ideas remain highly speculative and controversial within the physics community, but they illustrate how the dark energy puzzle connects to the deepest mysteries about consciousness, observation, and the quantum nature of reality. The fact that we exist in a universe where dark energy has just the right value to permit billions of years of cosmic evolution might be telling us something profound about the relationship between mind and cosmos. The far future of our dark energy-dominated universe presents scenarios that challenge human imagination and force us to confront the ultimate meaning of existence in a cosmos that may be heading toward eternal emptiness. If dark energy continues to behave as Einstein's cosmological constant, with perfectly constant energy density throughout space and time, then our universe is destined for what cosmologists call the heat death scenario. Over the next 100 billion years, galaxies outside our local group will gradually disappear beyond our cosmic horizon as space expands faster than light can travel between increasingly distant regions. The observable universe will shrink to include only the Milky Way, the Andromeda Galaxy, and a few dozen smaller dwarf galaxies that are gravitationally bound together in what astronomers call the local group. String theory provides potential mechanisms for such cosmic cycles through interactions between higher dimensional objects called branes. In the ekpyrotic scenario, our four-dimensional spacetime exists on a three-dimensional brane that periodically collides with other branes in a higher dimensional space. Each collision triggers a new Big Bang and begins a new cycle of cosmic evolution. These cyclic models offer the appealing possibility that our universe has no ultimate beginning or end, but instead undergoes eternal cycles of expansion and contraction. Each cycle could produce galaxies, stars, planets, and potentially life, making the cosmos eternally creative rather than destined for permanent emptiness. However, cyclic models face significant theoretical and observational challenges. The entropy of the universe increases during each cycle, and it's unclear how this entropy could be reset during the bounce phase. Without a mechanism for reducing entropy, each successive cycle would be shorter and less interesting than the previous one, potentially leading to a universe that eventually becomes too hot and dense to support complex structures. These galaxies will eventually merge under their mutual gravitational attraction, forming a single massive elliptical galaxy that some astronomers have nicknamed Milkomeda. But even this merged galaxy will be isolated in an ever-expanding ocean of space, with no visible connection to the rest of the cosmos. Future astronomers living in this far future universe would have no way to discover that a Big Bang ever occurred, or that billions of other galaxies once existed within their cosmic horizon. Star formation will gradually cease across the universe as the gas needed to form new stars becomes too diluted by cosmic expansion to collapse under its own gravity. The stars that already exist will continue to shine for trillions of years, but no new ones will be born to replace them as they burn out and die. Low-mass red dwarf stars, which burn their nuclear fuel very slowly, will be the last to shine, continuing to glow for tens of trillions of years. Eventually, even these longest-lived stars will exhaust their nuclear fuel and fade away, leaving behind a universe populated only by stellar remnants, white dwarf stars, neutron stars, and black holes. The universe will enter what cosmologists call the degenerate era, when the only sources of energy are the slow cooling of white dwarfs and the occasional flash when a white dwarf captures enough material to undergo a nova explosion. But even stellar remnants are not eternal. Quantum tunneling effects will cause protons to decay, with a half-life estimated at about 10 to the 34th years, roughly 10 trillion times longer than the current age of the universe. When protons decay, atomic nuclei will disintegrate, and white dwarf stars will slowly evaporate into space as leptons, photons, and neutrinos. The universe will enter the black hole era, when these gravitational giants are the most massive objects remaining. But even black holes are not permanent. Stephen Hawking's discovery of black hole evaporation through quantum radiation means that even the most massive black holes will eventually disappear, evaporating through the emission of Hawking radiation over timescales that make the proton decay lifetime seem brief by comparison. A black hole with the mass of our Sun would take about 10 to the 67th years to evaporate completely. Supermassive black holes containing billions of solar masses would persist for 10 to the 100th years or more. But eventually, even these cosmic giants will fade away, leaving behind only a sparse gas of photons, neutrinos, electrons, positrons, and other stable particles in an ever-expanding, ever-cooling universe. This ultimate fate, sometimes called the heat death of the universe, represents a state of maximum entropy where no further energy can be extracted to do useful work. The universe will have reached thermodynamic equilibrium at a temperature just above absolute zero, with matter and energy spread uniformly through space. No stars will shine, no planets will orbit, no complex structures will exist, and no information processing or consciousness will be possible. Yet even this bleak scenario assumes that dark energy behaves as Einstein's cosmological constant. If dark energy is instead a dynamic field like quintessence, the universe's fate could be dramatically different. Quintessence models allow for the possibility that dark energy density could increase or decrease over cosmic time, potentially leading to very different end states for our cosmos. In the phantom dark energy scenario, where the energy density increases over time, the universe would face an even more dramatic fate, the Big Rip. As dark energy becomes stronger, cosmic expansion would accelerate at an ever-increasing rate until it overcomes not just gravity, but eventually all the fundamental forces that hold matter together. The Big Rip would unfold according to a precise timeline determined by how rapidly the phantom energy density increases. Current observations suggest that if phantom energy exists, the Big Rip would occur roughly 22 billion years from now, though this estimate has large uncertainties. About 1 billion years before the Big Rip, dark energy would become strong enough to unbind galaxy clusters, causing them to disperse as individual galaxies race away from each other. About 60 million years before the end, dark energy would overcome the gravitational forces holding individual galaxies together, scattering their billions of stars across space. The Milky Way would be torn apart, with the solar system continuing to orbit our isolated sun as it races through the expanding void. Just 3 months before the Big Rip, dark energy would become strong enough to disrupt gravitationally bound systems like our solar system. Earth would be ejected from its orbit around the Sun, which itself would continue to shine briefly as an isolated star in the accelerating cosmos. In the final 30 minutes, dark energy would overcome the electromagnetic forces that hold molecules and atoms together. The rocky matter of planets would dissolve into a plasma of free electrons and nuclei, while biological structures would be torn apart at the molecular level. In the last fraction of a second, even atomic nuclei would be ripped apart as dark energy overcomes the strong nuclear force that binds protons and neutrons together. The universe would end not with the gradual fade of the heat death, but with the violent disruption of matter itself as space expands so rapidly that no structure can maintain its integrity. While the Big Rip scenario might seem like science fiction, it represents a genuine possibility allowed by our current understanding of dark energy. The key question is whether dark energy's equation of state parameter W is exactly -1, corresponding to Einstein's cosmological constant, or something more negative, which would indicate phantom behavior. Current observations constrain W to be very close to -1, but the uncertainties are still large enough to allow for phantom dark energy. Future precision measurements will determine whether our universe is headed for the gradual heat death or the violent Big Rip. fundamentally changing how we think about cosmic destiny and the ultimate fate of everything we know and love. But there are other possibilities that offer more interesting cosmic futures. If dark energy is truly a dynamic quintessence field, it could eventually change its behavior entirely, transitioning from acceleration to deceleration and potentially causing the universe to reverse course entirely. The quintessence field could reach a maximum in its potential energy and begin rolling back down, causing its energy density to decrease over time. If the quintessence field becomes attractive rather than repulsive, the universe could enter a phase of accelerating contraction, drawing all the galaxies back together in a cosmic collapse that mirrors the Big Bang in reverse. This Big Crunch scenario would see the universe shrink back to a singularity, potentially triggering a new cycle of expansion in what cosmologists call a cyclic or ekpyrotic universe model. Cyclic universe models propose that dark energy and the cosmic expansion represent just one phase in an eternal cycle of expansion, contraction, and rebirth. In these scenarios, our current accelerating phase would be temporary, eventually giving way to contraction as the quintessence field changes sign and becomes attractive rather than repulsive. The contraction phase would see galaxies approaching each other as space itself shrinks, stars colliding and merging, and matter becoming ever denser and hotter as the universe approaches a new Big Crunch. But rather than ending in a final singularity, some cyclic models propose that quantum gravitational effects would cause the universe to bounce back into a new phase of expansion, beginning another cycle with a new Big Bang. Current observations also show no evidence for the modifications to cosmic expansion that most cyclic models require. The cosmic microwave background radiation shows no signs of the gravitational waves or other signatures that would be expected from a previous contracting phase. While these observations don't definitively rule out cyclic models, they place strong constraints on their properties. The measurement of dark energy's equation of state parameter W over cosmic time will provide crucial tests of these different scenarios. Constant dark energy corresponding to Einstein's cosmological constant predicts that W should remain exactly -1 throughout cosmic history. Quintessence models allow W to evolve over time, while phantom energy requires W to be less than -1, potentially leading to the Big Rip. Current constraints from Type Ia supernovae, cosmic microwave background observations, and galaxy surveys limit W to be very close to -1, but with uncertainties of about 5 to 10%. Future surveys will reduce these uncertainties to the 1% level or better, potentially detecting small deviations from a cosmological constant that could reveal the dynamic nature of dark energy. The Dark Energy Spectroscopic Instrument, Euclid, and Roman Space Telescope surveys will each contribute complementary measurements that will collectively determine whether dark energy is truly constant or evolving over cosmic time. If evolution is detected, the rate and direction of change will provide crucial clues about the underlying physics driving cosmic acceleration. The theoretical landscape of dark energy research continues to expand as physicists explore increasingly exotic mechanisms that could drive cosmic acceleration. Some models propose that dark energy arises from quantum entanglement between widely separated regions of space, with the acceleration emerging from the breakdown of entanglement as the universe expands beyond certain critical scales. Other theories suggest that dark energy could be a manifestation of quantum corrections to gravity that become important only on cosmological scales. These models attempt to explain both dark energy and dark matter as geometric effects arising from the quantum nature of spacetime itself, potentially unifying two of the greatest mysteries in modern cosmology. The holographic principle has led to models where dark energy emerges from information theory rather than new fields or particles. In these approaches, the accelerated expansion is driven by the universe's attempt to maximize the information entropy stored on its cosmological horizon, providing a fundamental thermodynamic explanation for cosmic acceleration. Some of the most speculative ideas propose connections between dark energy and consciousness, or the anthropic principle. If observation plays a fundamental role in quantum mechanics, could the collective consciousness of intelligent observers somehow influence the value of the cosmological constant through quantum selection effects? While these ideas remain highly controversial and speculative, they illustrate how the dark energy puzzle connects to the deepest questions about mind, observation, and reality. Modified gravity theories continue to provide alternatives to dark energy explanations, proposing that acceleration arises from changes to Einstein's general relativity on cosmic scales, rather than from new energy components. These theories must pass stringent tests from solar system observations, while producing exactly the right amount of acceleration on cosmological scales. Recent developments in modified gravity include models with extra scalar fields that become important only in low-density environments like the cosmic voids between galaxy clusters. Other approaches propose that gravity becomes weaker on large scales due to interactions with additional dimensions or quantum corrections that modify Einstein's field equations. The challenge for all modified gravity theories is explaining why gravity would change its behavior at precisely the scales where dark energy effects become important. This apparent coincidence suggests that if modified gravity is the correct explanation, there must be some deep principle that connects the scale of cosmic acceleration to fundamental physics in ways we don't yet understand. Observational tests of modified gravity focus on measurements that can distinguish between the effects of new gravitational physics and true dark energy. The growth rate of cosmic structure provides one such test, since modified gravity models often predict different rates of structure formation compared to dark energy models with the same expansion history. Gravitational lensing observations are particularly powerful for testing modified gravity, since they directly probe how matter curves spacetime rather than relying on the expansion history alone. Future surveys will measure both the expansion rate and structure growth with sufficient precision to distinguish between dark energy and modified gravity explanations for cosmic acceleration. The search for dark energy extends beyond astronomical observations to include laboratory experiments designed to detect the particles or fields that might compose this mysterious component. If dark energy consists of a light scalar field like quintessence, this field might interact weakly with ordinary matter in ways that could be detected in sensitive experiments. Experiments searching for chameleon fields, which change their properties depending on the local matter density, use atomic interferometry and other precision techniques to look for violations of the equivalence principle or deviations from Newton's inverse square law. While no such deviations have been detected, the improving sensitivity of these experiments may eventually reach levels where quintessence interactions could be observable. Axion dark matter experiments, designed to search for one candidate for dark matter, might also be sensitive to axion-like particles that could compose dark energy. These experiments use ultra-sensitive magnetic field detectors to search for the conversion of axions into photons in strong magnetic fields. The Large Hadron Collider and future particle accelerators might produce evidence for extra dimensions or supersymmetric particles that could be connected to dark energy. While direct production of dark energy particles is unlikely given their incredibly weak interactions, high-energy experiments might reveal new physics that provides clues about the fundamental nature of cosmic acceleration. The profound implications of dark energy research extend beyond cosmology and fundamental physics to questions of meaning, purpose, and humanity's place in the cosmos. If our universe is truly dominated by invisible energy that will drive it toward eternal emptiness. What does this mean for the significance of life, consciousness, and civilization in the grand scheme of cosmic evolution? Some philosophers and scientists argue that the apparent fine-tuning of dark energy's properties provides evidence for design or purpose in the universe. The fact that dark energy began dominating at roughly the same cosmic epoch when complex structures like galaxies and planetary systems had formed, and when life was emerging on planets like Earth, seems almost too convenient to be coincidental. Others contend that apparent fine-tuning simply reflects selection bias. We observe a universe compatible with our existence because we couldn't exist in universes with very different properties. In the context of eternal inflation or string theory, landscapes with vast numbers of possible universes, it would be inevitable that some regions have properties compatible with complexity and consciousness. The dark energy puzzle also raises questions about the limits of scientific knowledge and human understanding. If the cosmological constant really does represent the energy of empty space, but quantum field theory predicts a value 10 to the power of 120 times larger than observed, are we approaching fundamental limits to what we can understand about nature using our current theoretical frameworks? Perhaps the resolution of the dark energy puzzle will require conceptual revolutions as profound as those that gave birth to quantum mechanics and general relativity. Just as those theories revealed that reality operates according to principles utterly foreign to everyday experience, understanding dark energy might require us to abandon cherished assumptions about space, time, causality, and the nature of existence itself. The story of dark energy research illustrates how science progresses through the discovery of ever deeper mysteries rather than final answers. Each question we answer reveals new puzzles that challenge our understanding in unexpected ways. The 1998 discovery of cosmic acceleration didn't just add dark energy to our inventory of cosmic components, it revealed that we fundamentally misunderstood the composition and fate of our universe. As we continue to probe the nature of dark energy through increasingly sophisticated observations and experiments, we're likely to encounter surprises that reshape our understanding of reality in ways we cannot currently imagine. The quest to understand why our universe is accelerating toward apparent emptiness may be the key to unlocking secrets of existence as profound as any ever discovered. The dark energy paradox represents one of the greatest intellectual challenges humanity has ever faced. Understanding why space itself possesses energy that drives cosmic acceleration, why this energy has the incredibly specific value required for complex structure formation, and what this means for our ultimate cosmic destiny will likely require insights that revolutionize our understanding of physics, consciousness, and the nature of reality itself. Whether dark energy represents Einstein's cosmological constant, a dynamic quintessence field, a modification of gravity, or something even more exotic that we haven't yet imagined, its discovery has fundamentally changed how we view our place in the cosmos. We now know that we live in a universe dominated by invisible components we barely understand, expanding into a future that may be radically different from anything previous generations could have conceived. The next decades of dark energy research promise to reveal whether our cosmos is headed for the slow fade of heat death, the violent disruption of the Big Rip, or perhaps the more hopeful prospect of cyclic renewal. Whatever we discover about dark energy's true nature will undoubtedly transform our understanding of the universe and our place within it in ways as profound and surprising as the discovery of cosmic acceleration itself.